Well, your quiz has been muted. All right, that's harsh. Are people not seeing the quiz? Yes. All right. I actually spent like 10 minutes trying to figure out a pun for the answer. Like that, there were good options. Frictionless. I know. But anyway. So okay. All right. Yeah, so that wasn't really kind of a good thing. Anyway, we're gonna do a little bit of a physics thing today, I guess, just because the fun never stops. So today they announced, I don't know if you checked the news, they announced like the new physics Nobel laureates for 2025. But neither of them were from U of T, so that's fine. Actually, I think it was three people. But last year, however, just exactly a year ago, October 8th, not exactly. So Jeff Hinton from U of T, John Hopfield from Caltech and Princeton had won the Nobel Prize. And it was in physics. It was a little bit weird because it wasn't really for physics. But that's a good thing because I get to actually explain what Jeff Hinton got the Nobel for, because it's actually kind of pretty accessible. So the connection. So of course, kind of Jeff Hinton is known for artificial intelligence, not really physics. He's not a physicist. However, he built on a model built by John Hopfield, who is a physicist, who also worked kind of like in early neural networks, and that led to Jeff Hinton developing the Boltzmann machine. The Boltzmann machine is like a little bit difficult to explain, but it's basically a more advanced version of the Hopfield network, which I am going to explain because it's not actually difficult. And at the same time, it's a really foundational and intellectually interesting discovery that happens to help to teach nested loops. So it's all great. So here's kind of how people thought about how you would store information. So people came up with a way to store information on whatever, like papyrus in Egypt or like tablets in Mesopotamia, stuff like that. And the way you do it is you write the information down, right? So you come up with symbols that represent basically sounds that represent in turn whatever is happening in your brain, right? So something like that. And like if you think about the brain as this kind of physical thing, you start thinking about, okay, like how is it going to store all those memories? Like how do I remember that project one was due last week and yesterday was the physics midterm, and I have like all my plans for the weekend, things like that, right? So I think the most natural thing for people to do, if they're just thinking about how they usually store information, is, well, like it's writing something down, right? And that is how we were doing it in Python. So to kind of belabor the point a little bit, how do you store information? Well, you say, okay, like pi is whatever, right? So like 3.14159, whatever, right? So we haven't spoken exactly about how that's stored in a computer, but it's basically stored the way you would store it when you're writing something down, right? So you say, okay, like we are storing the digit 3 and then the digit 1 and then the digit 4 and so on, right? So that might be how you would think about, well, like it must be that that's how the brain works. that creates all sorts of issues. So for one thing, the brain doesn't really look like it's like a page of paper or something where there is like blank space where you can just write stuff down. It's like a fixed thing. So intuitively, that seems like a problem. The other problem is even if it were like Robert's library or something where there's shelves on which you can put books, that's clearly not how memory actually works because you can retrieve memories, quickly. You don't have to say, okay, like I'm looking for this piece of information that's somewhere in Robert's library. So I'm going to like, is it here? Is it here? Is it here? Is it here? Or I found it. That's like clearly not how it works. There are ways to get around this. For example, there's computers and robots which help you find the relevant information or like help you point to the relevant book. So there's clearly ways of doing it with computers, right? But it seems like it's a difficult problem. It seems like we don't know how the brain works exactly, but it seems like this kind of mental model of, oh, it's just a bunch of shelves with books with pages in them with things written down in them is not what is probably going on because of all those issues with retrieval. And that's before we get to what you retrieve is usually approximate. It's not exact. So it's clearly not that you're like literally going and finding, what's the hundredth digit of pi. That's a slightly bad example. Some people do know the hundredth digit of pi, but for most of the things that you retrieve from your memory, it's not going to be exact, right? So here's an idea. So that was Hopfield network, and like I said, so developed by John Hopfield. That was the first attempt. It works. You'll see how well or not well it works. Not that well. Nevertheless, it led to the development of a better model of how you might store memories, and that was historically really significant. Even though kind of ChatGPT does not directly have to do with Boltzmann machines. It's more like Boltzmann machines were like historically significant in being able to train early versions of deep neural networks. They're not actually currently used, but that's fine. So, okay. So here is the thing. So a Hopfield network. So if you haven't seen a diagram like that before, that's called a graph. So a graph is basically a bunch of nodes. So the nodes here are circles, and they're connected by what's called edges. And those are just the arrows. So all this picture is saying is I have three nodes in this case, so x0, x1, x2. And they are connected by those edges. So x0 is connected to x1, and x0 is also connected to x2. That's why there's an arrow here. And then there is a strength of the connection that's specified. So the strength of the connection between x0 and x1 here is S01, a number. Okay, so this is just a picture. So we have three things, three numbers, if you like, x0, x1, x2. And so in this case, the connection goes from x0 to x1, not x1 to x0. And then there is a weight in the connection. So what's connecting x0 and x1 is S01. So this is like it goes from 0, it goes to 1. So that's why it's S01. This one goes from 0 to 2. So that's S02. All right. So what we want to do is we want to store memories in this kind of thing. So the memories here would be 3-digit sequences or like 3-number sequences. And the way we're going to do it is we're going to define what we want to call it's like a vague analogy to kind of thermodynamics. So it's called the energy function. It's not like energy in a way that, like potential energy is energy. There are systems. So like so this is like not something that you'd see until maybe second year, if then. So there are things where if those are like charged particles or something, and they're like arranged in a lattice, then depending on the distances, there's like different potential energies, stuff like that. But just think about it as a formula. So going back to the memory. So we define this energy function. So the energy function is going to be the sum of xi, xj, sij for every possible combination of xi and xj. And we are just defining the mechanism of storing memories is saying we have this energy function and we are defining the memories as the minima of this energy function. Okay, so here's an example. So I have my specific network. So x0, x1, x2, those are variables. They can be, 1 and -1. So the energy here is going to be like this. So x0 times x1 times 2, and then x0 times x2 times -1. So that's this term. And then x1 times x2 times 1. So that's this term. So this is just like a formula that comes out of this. And then we're saying, okay, like there is like different possible configurations of x0, x1, x2. Some of them correspond to the minima of this energy function, and some of them don't. And we are saying we want for the memories to just be defined as the minima. Okay. So the idea here is if I were to change this to something else, then the minima could potentially be different. So that would mean that I'm using those weights in order to represent what the minimum might be and what the memories are. Does that make sense? So why would I do any of that if I could just write down, if I could just say, I want to just write down that I remember that like this is a thing and this is a thing and this is a thing and this is a thing, nothing else is a thing as a memory. Well, because what I want to do is I want to be able to just keep those three numbers, 2, 1, -1, as the things that I actually write down. And then I want to be able to store new memories and I want to be able to retrieve memories. Ordinarily, I would not be able to do that with just three numbers. With this, you can actually do it because you're just saying, give me the weights, and then whatever corresponds to the minimum of this guy, that's my memories. Whatever doesn't is not. And here you can just check that those really are the minima of this thing. So x0, x1, x2 must be like either -1 or 1. So, okay. So how would you store and retrieve memories using this kind of thing? Well, to retrieve the memories, you just take this and you say, which x0, x1, x2 minimize this. To store a memory, that's more complicated, right? So what you want to say is, I don't want to be forgetting things. So I want to keep all my current minima. I want to adjust the weights so that I also have my new minimum that would correspond to a memory. And I also don't want to create spurious minima. So I don't want to create basically like hallucinations. How do you do that? Well, like basically the idea is if you adjust the weights just so that the new minimum is actually a minimum, and you can like figure it out. You'll see that in the lab this week. So you would just say, okay, like I want for x2 and x1 to be the same. So that means that I want this weight to be positive. If I want x2 and x1 to be the opposites, then I want this to be negative. So depending on what my memory is, I might like push the weight a little bit up. If I want for x1 and x2 to be the same in my new memory, I might like to push the weight a little bit down if I want x2 and x1 to be the opposites. And then it turns out that I can push the weights a little bit to the right, a little bit to the left, just enough that I ordinarily would be able to store new memory without forgetting stuff. So without making it so that the old minima are not the minima anymore. And also so that I don't create false memories. So don't create minima that are not actually what I intend to store. So that's kind of the idea. So let's implement it. Before we implement this, so is the idea kind of clear? So we want to store, just to reiterate, so we want to store those sequences of ones and minus ones. And the way we do it is we define those weights. All right. So if we find, so the idea is that if we find the weights, like for example, -1, 1, 2, or something like that, in such a way that the minima of this energy function correspond to what we want to store, then we've succeeded. So does the goal make sense? Okay, does the goal not make sense? Yes.
Is it just like,
Hello. Were you watching the dancing guy or something? All right. Doing it well. Whatever. You're here. That's what's important. Yeah, you had a question.
wait, so just like you're just like counting to one. Like you're tapping to one node.
Say it again.
Is it more like you're just tapping to one? That's stuff. And you want to store your value into that node.
No. So the question was like, do we want to store the value into a specific node? So no. So what we have control over is the numbers -1 to 1. What we want is for the minima of this energy function to correspond to true memories. Right? So we control the weights, those three numbers. And what you want to get out of this is the minimum. So we kind of implicitly store the data by adjusting the weights so that the minima are the true memories. That's the goal. We haven't actually done that yet, right? So that's just the goal. Yeah.
Why is there a negative sign in front of all the
Okay. So there should be a negative sign here. There should also be a negative sign here. It's just that that's a typo. Yeah. So like if you remove the negative, you could just say I want the maxima rather than the minima, but ordinarily you say the minimum. Yeah. So we are trying to make it so that, so this equation is set. We are trying to make it so that the minima happen to be the true memories. Yeah, so like if you compute the minima, then you want for those guys to be the min. So you want, so like this thing has like some minima, some whatever, non-minima, non-maxima, whatever, right? So what you want is you want for the minima to correspond to, oh, more people. So you want the minima to correspond to true memories. And you want everything else to not be minima if it's not a memory. Right? So like that's just the goal. Yes. Sorry, I cannot hear you. Yes. So in this set, so like there's like various flavors of this, but yes, kind of in this setting, you want x0 the axis to be either -1 or 1. So because this allows you to actually be able to do things, if you make them real numbers, the task becomes much harder. So it is kind of generally true that like if you're able to store, a sequence of -1s and 1s, you can encode any information that you want. So we'll see that more in 190, but the intuition is okay, like if you're able to store like 100 zeros and ones, that allows you to store like a lot of information. All right. Okay. So we had like 25 situation. I think, however, that's probably about half of you want to hear the explanation again. So I think we'll do it maybe slightly faster because the people who came in, that's a little bit on you as well. Okay, so what we're talking about is the Nobel Prize was just announced for 2025, but not for U of T people. So we are doing last year's Nobel Prize for Geoff Hinton. And specifically, we're talking about actually John Hopfield's work, which is a precursor to Hinton. John Hopfield shared Geoff Hinton's prize. So the idea is that, sorry, I'm going to repeat it. There's like too many people. So the idea is that we want to think about how the brain might be storing information. And the idea is that the brain is probably not storing information the way, the ancient, Egyptians, Chinese, Mesopotamians figured out how to store information, which is like writing things down on paper. In part, one of the intuitions is that if you write a bunch of things on paper or like on a tablet or something, like the clay tablet, then it's going to be really difficult to retrieve it, right? So you are able to just hear like, how did you do on the physics midterm? And right away, like, you get an idea of how you did on the physics midterm. You don't need to go back and look at all your memories from life, like, like how was my first day in school? Like what am I gonna eat for dinner? No, like you focus on the physics midterm right away. So there is this kind of fast retrieval mechanism. It's also just like doesn't seem like there's like empty space in your brain where you can write down new stuff. That is probably why you didn't remember stuff for the physics midterm yesterday. So this is kind of a model for how the brain might work. That's like somewhat plausible. And like I said, so it's like historically important. It's not currently used in kind of state-of-the-art neural networks. However, in the 2000s, 2010s, it was important for the development of current deep learning methods. So the idea is like this. So this is called a graph. And this is what we're going to use in order to store information. So a graph is basically a bunch of nodes. So nodes are like circles. And they're connected by what's called edges. So those will be the arrows. In this case, they're weighted. So each arrow here, each edge is associated with a number. Like S01, for example, is a number that's associated with the connection between X0 and X1. All right. So here's how storing and retrieving memories is going to work. We are going to have what's called an energy function. There is a vague analogy to the kind of energy you see in thermodynamics here, but you can just think about it as, just a function. There is a missing minus here, which will appear on the next slide. Thank you for your note. So the idea is like this. So this picture corresponds to this formula. We're just saying if this is the picture, then the energy is just a formula. And the formula is x0 times x1 times s01. So like the 0 connects to the 1 here. So that's why s01. And then plus x0 times x2 times s02. So s02 connects x0 and x2. And plus x1 times x2 times s12. So from 1 to 2. So that's why it's s12. All right. And then we're just saying, okay, we're just defining the memories of this thing. This is called the Hopfield network as the minima of this energy function. This is missing the minus, so this would be the maxima. Okay, so here's a concrete example. Let's say that we have a network that's defined like this. So a network that's defined like this, like that just means that the energy formula is like this. So this is like 2 times x0 times x1, because the 2 connects x0 and x1. and then x0 times x2 times -1, so that's this guy, and then x1 times x2 times 1, so that's this guy. And then if you work it out, so x0, x1, x2 here can only be -1 and 1, then it happens that those are the minimum. Like you can just check. There's not very many to check. Okay. So the idea is that instead of explicitly saying those are our memories and we're just going to write them down, we are instead going to write down the structure and the -1 to 1. And out of that, the minima are going to fall out automatically if you find them. All right. So why do that? Well, because that allows you to do storing and retrieving memories in a way that kind of is more kind of biologically plausible and kind of more approximate. So how would you retrieve your memories from that? Well, you just say, okay, this is the energy function. Find the minima, whatever the minima are. Those are the memories. So storing, you'll see in the lab, that's more complicated. So if you want to store new memories here, what do you want to do? You don't want to forget old stuff. So that means that you want to adjust the weights a little bit so that the old minima is still the minima. But you also want to make it so that you adjust the weights just a little bit so that the new thing that you want to store is now also a minimum. An additional constraint is that you don't want like what you might term hallucinations. So you don't want for a new minimum to appear that doesn't correspond to an actual memory. So the job is you have this formula which defines the memory by saying the minima of this formula are the memories. And you want to adjust it just a little bit so that the old minima are preserved, at least approximately, and so that there is no new spurious minima, and the thing that you want to store is also a new minimum. You'll see exactly how to do that in the lab, but the basic idea is like in order to keep the old minima, like you just don't want to change this too much. So you don't want to change the -1 to 1 all that much. You want to adjust them just enough so that were you all guys standing in line on King's Court Circle? All right. Were you? I know. Nobody says anything. So Ben says office hours. All right. So okay. You're gonna have to watch the video because I already restarted once. So okay. So okay, all right. So, but for the people who just came in, you do need the context, but I'm gonna switch to coding and I'm just gonna code it up. So the goal here is to take this structure, transform it into this formula, and then just find the minima of this formula. And that's just a computational task, right? So let's do that. Okay. Thank you to Ali. Okay. So this is what we have. So what I want to do is I want to take this and transform it into the energy function. So the energy function is, again, like this times the weight, plus this times the weight, plus this times the weight, all minus. So I'll say energy. And that is going to be, so it's going to take x0 and x1. Let me do like x, and let me do s, like this. So x0 and x1 and x2 are going to be just, x0 and x1 and x2. And then s are going to be, so here I'm just going to define it as like so this is going to be s01, right? And I'm going to have s02, and I have an s12. So I'm gonna define it like this. So in order to make it work, I need to actually do a little bit more, right? So the x is not that difficult. The s I need to set up. So how can I set up s? I can, for example, say, okay, so like in general, that's going to be like a 3x3 thing, but not all of the s's are there, right? So like I have an s01, but I don't have an s10. So I'll just write it like this. So s01 here is 2. And then s02 is -1. And then we said s12 is going to be 1. So those are the things that are actually written down. Does that make sense? Just because like I want to say s01, so the thing that connects 0 to 1 is 2. The thing that, so the arrow here is like 0 to 2, so that's s02, so that's -1. And then s12, so the arrow goes here, so that's the 1. And then everything else is going to be just nothing. So for nothing, I'll just write none. Does that make sense? All right. So what do I need to do now? I can basically say, okay, so if this term is none, it doesn't count. If it's not none, then I'll add it to the energy. So I'll say, okay, the result is like this. Initially, it's 0, and I'll keep adding stuff. So I'll try every possible connection. So like x0 to x1 exists, x0 to x2 exists. There is no x2 to x0. So, but I'm just trying every possible pair of x's. That's exactly what we had done last time. So every possible pair of x's. So that's like every possible product xi at j, xj for i0 to 2, j0 to 2. That's something that we know, right? So we say for I in range length x, and we say for j in range length x. And that makes it so that we now have xi times xj as a thing, right? So that lets us get every possible xi times xj. So we're going to say, okay, so if s at I at j is not none, then that goes into the energy. Like so. And we return minus the result. Does that make sense? So we have x0, x1, x2. That's an input. We have the s's, which are stored in the table. Not all the s's are there. So like not everything is connected to everything. And we don't have like anything on the diagonal. So like we don't have like x0 times x0. So here, this is none, this is none, this is none. Right? But if we have an arrow, then we get the corresponding weight and we have the corresponding product. Make sense? So that's the energy. So now we want to retrieve the minimum. So if we retrieve the minima, we don't know the x's. That's what we're trying to find out. We know the s, right? So the s is what stores the information. The way we get the information back is we say, okay, the s encodes the information using the weights. We're getting the information back by finding the energy minima. So in general, finding the energy minima is actually quite difficult. But here, there's just not very many possibilities. So we'll just find the smallest, we'll just find the x's that correspond to the smallest energies. Those would be the minimum. Right? So how do we do it? Well, what are all the possible x's? Well, it's like, like -1, -1, -1. And then like -1, -1, 1, and so on, right? How do we find all the possible, how do we enumerate all the possible x's? That's the same as all possible passwords, where the possible characters are -1 and 1. So I'll just say, I want to find all the possible combinations of x0, x1, x2. How do we do that? That's exactly all possible passwords. So we're saying for x0 in -1, 1. So that just says like x0, make it -1, then make it 1. And then we say for x1 in -1, 1. And then we do like x2 in -1, 1. So that makes it so that we get all the possible combinations of the x's. So now that we have like x0, x1, x2, we can build the x. And now that we built the x, we can send it to energy and say, what's the current energy? Like so. Right? So that computes the energy for every possible x. Let's try it. I don't think we're going to be done today, but that's okay. So I'll say x is x. And current energy is current energy. And now I can just call it. So I already defined x. S. So S is what tells me what the memories are implicitly. And now I'll call my kind of retrieve minima. That's not quite retrieve minima. And here's what I get. So as you see, we have -2 as the smallest possible energy. And we have this guy, and we have this guy, and we have this guy, and we have this guy as the minima. So those would be the memories. So we haven't quite retrieved them yet. We'll do it next time. But you can do it kind of by hand. So just to show you what would happen if I change this stuff a little bit. So the whole idea is that you want to be able to control the memories by changing those real numbers. So if I change it to like -1.1 or something, it looks like this, right? So at this point, it's not exact. Like, of course, I made it like a fractional thing, so it would be weird if the energies kept being integers. But you can kind of see that changing this a little bit doesn't change the outputs all that much. And that's the key. So we are able to store, in this case, 4 memories in just 3 numbers. And if we modify those numbers, we are able to, in principle, store memories, possibly remove memories. That actually works the same as storing, just the other way. And kind of the key here is you can adjust those a little bit so that you create new minima. So here, like not enough, but like if you change it a little bit like this. So here, like those now kind of get to be negative as well. So you can see that if you adjust those things, you can potentially create new minima so that you're still using just 3 numbers, but you're able to store different amounts of memories, and you're able to remove, you're able to add. You'll see more of that in the lab. All right, I'm done. You can go back to King's Cloud Circle. Yeah. All right. All right. See ya. Right. Thank you.